Okay, so hello everyone. Welcome to our this week Rubbers in Efficient AI seminar. And today we're glad to have Professor Kanad Basu from the UT Dallas to give us this talk about the functional safety of the deep learning hardware. And Professor Basu received his PhD from the University of Florida. And his thesis was focused on improving signal observability for post-silicon validation. And post-PhD, Professor Basu worked in various semiconductor companies like IBM, Synopsys, and he also had an internship at the Intel. Currently, he is assistant professor at the Department of the Electrical and Computer Engineering of the University of Texas at Dallas. And he leads the Trustworthy and Intelligent Embedding System Lab. And prior to this, he was assistant research professor at the Electrical and Computer Engineering Department of the NYU. And he has authored one book, 2 US patents, 2 book chapters, and several peer paper reviewed journals and conference articles. And he won the Best Paper Award at the International Conference on VSI Design in 2011 and the Honorable Mention Award at the VSI Design 2021. And his research has been covered by several news agencies, including NBC, CBS, and so on. And Professor Basu's current research interests are functional safety, hardware and system security, deep learning hardware, and quantum computing. And his research has been funded by the NSF, SRC, and the DARPA. And now let's welcome Professor Basu to give us this talk.
Thank you. Thanks a lot, Dr. Yuan. So today my topic is towards functional safety of deep learning hardware accelerators. Let's first understand the need for deep learning hardware accelerators briefly, although I believe a lot of you might already have the knowledge of why it is used. And then we will go on to what is functional safety and why it is important in deep learning hardware accelerators. So this is an outline of my talk. First, we'll briefly go over the basic challenges of machine learning. We'll go for the introduction of deep learning accelerators like tensor processing unit. We'll talk about faults in DNA accelerators and functional safety violation detection, as well as mitigation techniques. So machine learning has been there in various domains in our lives, right? Like, for example, for self-driving to machine translation, to playing complicated games and artistic style transfer. In fact, a few years ago, Google's DeepMind London office, their computer defeated the best Go player in the world. So we have these machine learning systems which are going all over the world, accessing different aspects of our everyday lives. Now, let's briefly go over the basics of neural networks, which are the basic points of machine learning. I believe all of us know this, but just a revision. So we have multiple layers of neural networks where the number of nodes in each layer is denoted by n in L. And each layer has some activation layers, there's a weight matrix and a bias dimensions. So basically, you multiply the weight with the activations and then add the bias and then pass it through an activation function, which goes into for the next layer. Right? So traditionally, the costliest operation for inference networks are the dense matrix multiplication operation. The matrix multiplication operation scales worse than any other operation. It's order of n cubed. It's even more a bottleneck as problem scale. So at the end of the day, most computation becomes dense matrix multiplication. So that's one of the bottlenecks that we really need to address for machine learning applications. So what are the challenges of deep learning models? First, it's hard to distribute models, right? Like in 2012, when we had AlexNet, that had 8 layers and 1.4 gigaflops. Now we have ResNet in 2015, which had 22.6 gigaflops. Now, when you're trying to transfer this model to a small edge device like a cell phone or an UAV, it becomes increasingly difficult because of this large model. The other problem is the long training time. Almost all of us who use machine learning, who use these classical networks like ResNet and all, we use the trained networks and we try to retrain them or use it for any other research. But if you try to train a network from scratch for any other purpose, then it becomes exceedingly difficult, right? The training time is like 1.5 weeks, even on GPUs. So that becomes really, really difficult. So how can you actually address this issue? The other problem is energy efficiency. So this article came out in 2019, which says that creating an AI can be 5 times worse for the planet than a car. So we know that pollution and energy efficiency are very imperative to our very survival of the human race. So therefore, we need to have more sustainable models for AI development. So these are the main challenges which promoted researchers to look beyond software implementations of AI and look for hardware accelerators. So what are hardware accelerators? So hardware accelerators are dedicated hardware units that are used to run AI applications. In 2017, Google developed their famous tensor processing unit, or TPU, which are 30 to 80 times faster than CPU or GPU. So what does a TPU do? A TPU is a hardware which is not a general purpose hardware. It runs specifically a deep neural network, right? Like you cannot run Zoom that we are using right now, or I'm using Microsoft PowerPoint. You cannot run that on the TPU. On a TPU, you can only specifically run deep learning applications. Now, why do we have hardware accelerators and why do we prefer hardware accelerators? So since Moore's law is not being obeyed anymore, people are trying to think that instead of scaling down the size, why not make dedicated hardware for particular application? So this can be cryptographic hardware, machine learning hardware, or any other application. So these hardwares are customized for this particular application. Like, for example, TPU is customized for deep learning applications. So it will provide the least area overhead. On the other hand, it will provide the minimal energy overhead as well. So you are totally customizing a hardware for an application. It's not like your CPU or the GPU that you use in a regular computer, which are more general purpose. You don't have that facility in a TPU. So how does a TPU look like? And by the way, I'm talking about TPU, but most deep learning accelerators follow the same hardware architecture, okay? So the TPU actually consists of several MAC units or multiply and accumulate unit. Now, what is a MAC unit? As you can see in the insert here, the MAC unit is actually, it does a multiply and accumulation. So we just explained in few slides back that the matrix multiplication is the most costliest operation in AI, right? In machine learning. So what we do is we multiply the accumulation, the activation and the weight, and we add it to the previous stage. So basically, we have a weight memory from where the weights are fitted in, we have an activation memory from where the activations move horizontally, and then they are added together and then trickle down. This helps in reducing the complexity of this whole matrix multiplication operation. A typical TPU has 256 cross 256 MAC units, but of course, you can develop your own accelerator with a reduced number of MAC units, okay? Let's take a few moments to understand how this matrix multiplication works. Let's take a moment to understand of the systolic array operation. This is, by the way, called a systolic array. And we're ignoring the bias for now. Let's focus on just the matrix multiplication, the activation and the weight, okay? Suppose we have this and we have a small 3x3 systolic array for explaining this. So these are the activations, and see the activations come in here. In the first cycle, the weight W11 gets multiplied by the activation A11, which trickles down step to the next MAC unit, which is W21. Then it is the W21 is multiplied with A12 and it's added to the partial sum of W11 plus A times A11. So we get a new partial sum, which in the third cycle, it adds the W31 times A13. So as a result, this goes in a cycle by cycle manner, and you can reduce the complexity much more, okay? But this is how a typical systolic array operation works. Now, apart from these architectures, the people have proposed something called in-memory computing. So the high energy and latency required for the data movement between the memory and the processing unit, that leads to the von Neumann bottleneck. So as we were mentioning about the systolic array-based architecture, it's very efficient compared to a CPU or GPU, but still there's a problem, right? Because you have to need a lot of energy to move the weights from the weight memory or the activations from the activation memory all the way to the MAC units. How to overcome this? So people proposed a new technology called processing in memory. So basically what they propose is you do the computation inside the memory. You do not have a separate memory and a computation unit. The computation is performed as part of the memory. So this is a new computing paradigm that performs both storage and computation in the memory unit. And this promising technology for next generation AI for neuromorphic computing, several hardware support has evolved over time, like SRAM, DRAM, Flash, RRAM, memory-based technologies, and so on, right? And in fact, some of the famous semiconductor companies like Intel is also exploring these. And there have been various startups in this domain of in-memory computing for machine learning or neuromorphic application. Now, DNN accelerators are being proliferated. Actually, if you see an automotive SoC, which is an ADAS SoC on the left, you can see that we have a vision accelerator which does. And the AI-enabled shipments have been increasing over the time, and it's predicted by 2025 they will go on some trillions of devices. Now we understood why AI accelerators are needed and how AI accelerators work. Now let's focus on the topic of today's discussion, which is functional safety. So faults in a DNN accelerator are highly detrimental. So when does fault occur? So faults can occur due to various reasons. There can be undetected faults in a device, and that can happen not only in DNN accelerators, that can happen in any device. Okay, so that can happen in any device, that can happen in your computers, that can happen to your cell phones. Faults can happen due to undetected faults obtained from the testing, latent defects due to aging. When your device ages, there are faults, or due to single event upsets, right? Now, see the classification accuracy in the presence of faults. We did this experiment, and we showed that the classification accuracy actually plummets significantly. So if you see, we trained some MLP using MNIST and TIMID dataset. So for the TIMID dataset, you can clearly see that with a 4% faults, sorry, 0.004% faults, only 4 faults, the accuracy plummets from 79 to 41%, which is a huge reduction. Now, what does this imply? What is the physical implication of this? Now, let's imagine a hypothetical scenario where your laptop, so you are listening to our presentation today, and your laptop due to a fault crashes. What's the worst thing that can happen? You will not be able to listen to this talk. You will probably lose some data, but you might not lose data if you are storing it in the cloud. And you might have to spend some more money to buy a new laptop, right? That's the worst thing that can happen. Now imagine when you have a self-driving car and the AI accelerator has some faults. What's the worst thing that can happen? If somebody is driving on a highway for some, say maybe 70 miles an hour, and there's a fault and there's a wrong classification, then that can actually lead to loss of lives, right? Like, for example, if there's a stop sign, not on a highway, on a regular road, if there's a stop sign and the accelerator doesn't recognize it correctly, it doesn't stop, then that might hit somebody, right? That might lead to an accident and loss of human lives. Similarly, imagine a situation for military or Air Force or Navy. So if this type of things happening, for example, the latest war between Armenia and Azerbaijan, that had more drones or more non-human components than human components, right? That was the first war in the history of human civilization, which had more machines than human beings. So if one of these things happen in one of these UAVs that are being used during war, then that might be a concern for national security. We might end up losing the war, which we cannot afford, right? So this is much more relevant when you are looking for a mission critical application rather than an end user application, right? Same thing, you can think of smart medical devices like a smart pacemaker or a smart insulin pump. If the smart insulin pump has some, the machine learning unit has some fault and does some misclassification, that might actually lead to the death of the patient, which we really do not want. So to prevent these things, functional safety is a technical solution that has been proposed. It has been put forth by the ISO 26262 standard. Although it was proposed for automotive, it is now extended to various other applications like maritime, industry 4.0, medical, etc. Right? So what is functional safety? It says that when fault occurs, the fault should occur in a safe way, that it should not lead to an unsafe or damaged human lives. So it controls failures to achieve or maintain a safe state, and the scope is now broadened to encompass other mission-critical applications. Now, faults can lead to highly disastrous consequences. So as you can see here in this picture, if you have an original speed limit of 35 and due to fault, you are getting a value of like 85, then that might lead to an accident and loss of human life, right? So in this talk, we will define any degradation as FUSA violation, right? Or functional safety violation. Functional safety in industry is also called as FUSA. So we call it as FUSA violation. So it is highly imperative to maintain the FUSA in DNN accelerators, okay? So first, we will explain what is the impact of FUSA violation on various parameters of a machine learning model. Okay, so to do this, we provide an extensive bit level analysis. We consider Google's TPU as the baseline systolic array with DNA accelerator. But as I have mentioned, you can do on any other DNA accelerator. Some parameters will change, but overall inference will probably not change. We quantize the weights and activations to 8 bits. The multiplier output is 16 bits quantized, and the accumulator output is 24 bits. For this experiment, we consider a very simple network. We consider an MLP with 3 fully connected hidden layers and 256 nodes in each layer. It can be extrapolated to other network architecture, but we wanted to give a basic idea of what happens when you have different variations. That's why we use this very simple model. We only consider data path faults. We consider the faults as stuck at faults, mapped as stuck at faults. So stuck at faults means a value is stuck at either 0 or 1. Now, in traditional testing methodology, they can be stuck at 0 or stuck at 1, but we focus on stuck at 1 because there are 2 observations we did. We noticed that the faults are more prominent if the faults happen at the most significant bits of the weights, activations, multiplier, and accumulator outputs. And since most significant bits in most of the values are 0, we consider stuck at 1 fault. So we are trying to look at the worst case scenario, right? What happens in the worst case scenario? So this is bitwise vulnerability analysis. So if you have, say, several bits, right? And what happens in the accumulator is 24 bits. So what happens if you have faults in the MSB all the way to the LSB? What is the impact? So as we can see, after having faults in 7th bit, the impact of faults is reduced. So the first 7 bits are the most vulnerable. But the interesting thing to note here is if you have a fault in the MSB, that actually results in almost more than 30% reduction in accuracy. Then we have faults in the weights and bias. So we have unit-wise vulnerability analysis in weights, bias, accumulators, and multipliers. So in the weights and bias, we can see that if you increase the number of fault units, there's an accuracy drop, but this accuracy drop is not significant though. It's like still in borderline range if you have low faulty MAC units. Typically, the number of faulty MAC units in real-life scenario cannot be more than 4%. So at 4%, we have like 2.5% or 3% accuracy drop, which is quite sustainable. However, for multiplier faults, it's not the case. So as you can see in the multiplier faults, if you have a fault rate of, so for 100 multiplier faults, the fault rate is almost 20% drop. So this is huge. On the other hand, for accumulator faults, so just 5 faults, you can have 80% accuracy drop. So the baseline accuracy, as we all know, for MNIST and MLP is something around 98 or 99%, right? Now, if you have just 5 accumulator faults, that drops the accuracy to more than 80%, that's a very scary scenario. That means your MLP system is not at all working perfectly. So this is a cause of real concern. We also did an analysis on activation. So basically what we did, we kept everything same in the models. We just changed the activation functions. So we kept the same number of hidden layers, the number of nodes in each layer, the same data set for training and everything. And we looked at the various activation functions. And we clearly see that ReLU has the highest accuracy drop compared to TANH and sigmoid. So if you change the activation functions, the functional safety violation changes. Then we changed the data set. We used 3 different data sets, MNIST, Fashion MNIST, and Cypher10. And as you can see, the accuracy drops of MNIST and Fashion MNIST are much more prominent than Cypher10. One of the reasons is that the Cypher10 baseline accuracy is itself pretty low. So when you introduce more faults, the accuracy drop in Cypher10 actually doesn't degrade significantly. Now, we'll talk about DRAM faults, memory faults. So DRAMs are used as main memory subsystem in the sparse DNA accelerators, okay? So basically, a lot of DNA accelerators have a lot of 0 weights. So to use this, these sparse DNA accelerators use DRAMs. Now, DRAMs consume a significant amount of energy, both in active and standby state. So although we can increase the refresh interval to address this, it results in persistent errors. So if you do not change the refresh intervals, it incurs a lot of energy. If you change the refresh interval, it can reduce the energy, but it leads to a lot of persistent errors, which are called VRT, variable retention time errors. Okay, so this is the DRAM architecture, and these variable retention time errors arise from the non-idealities. So as you can see for different temperatures, you can have a different number of bit flips. So the percentage of error rates, if you increase the refresh interval, then it changes drastically. So we can have two types of errors, anti-bit and true bit. So anti-bit flips are from 0 to 1 and true bit flips are from 1 to 0. So you can have both these types of errors if you increase the refresh interval. Now, this can actually potentially lead to a lot of errors. So we have two types of mapping, memory bitmap and compute bitmap. So what these bitmap encodings do in a sparse accelerator. So when you have a 0, that means you are not doing any computation. When you have a 1, that means you're doing a computation. That's how you stored the sparse matrix, right? Now, what happens if due to a fault, due to this refresh intervals, a 0 changes to 1 or a 1 changes to 0? If a 0 changes to 1, that means there was no computation, but you're forcing it to do a computation, so that does some garbage computation. On the other hand, when a 1 changes to 0, that means you are negating a valid computation. So you are not doing a valid computation. For the final computation actually changes really badly and you get some bad results. So as you can see, in scenario 1 and scenario 2, you can have both these faults and you can have this type of wrong computations. So we look at the faults, impact of faults on the memory bitmaps of sparse DNA accelerators. So we can see that the accuracy drop for increases significantly, and that's not only true for MLP. We also did on LENET and VGG16, and as you can clearly see, the accuracy drop increases significantly when you increase the number of faults. When there are error in compute bitmaps, as you can see, the accuracy drops also significantly for two. We did the experiment with two designs, MLP MNIST and Fashion MNIST, and LENET Fashion MNIST and VGG16 Cipher 10. So in both cases, we see that compute bitmaps increase significantly changes the accuracy drop. Okay. So now if we have errors in the trained weights, what happens if the trained weights have some error, not the bitmaps? If you have faults in the weights, then accuracy drops are there, but these are not significant. There are less significant accuracy drops that we can see when there are change in weights. Okay. So those are our observations we had obtained. So the inference we can draw from here is that DRAMs also play a significant role in reducing the accuracy of the functional safety of these deep learning accelerators, right? You have to maintain a proper DRAM refresh interval in order to ensure that these things do not occur. So now we will talk about the next part, which is functional safety violation detection. Okay. So what is functional safety violation detection? So see, we have now talked about what type of faults can occur and what type of violation detection can occur. Violations can occur. Now you need to detect them, right? Like not all violations will lead to fault effects. Let me give an example. Suppose you are running a machine learning on MNIST dataset, right? Say if you have an image of the number 6. For a fault-free machine learning network, let's say your confidence level for the level of 6 is say 90%. And when you have a fault, the confidence level drops to say 70%. But still your prediction is correct. So you don't need to worry about that. But for some other images, that might actually result in misprediction. So you really need to detect these faults. You really need to detect whether some function safety violation has happened before that actually results in an error and leads to an accident or loss of human life. So to do that, we present a software-based self-test scheme to detect the presence of such faults. So basically what we do, we have functional test pattern which belong to a particular class of data, and these can be used for detecting faults. Okay. So why don't we use traditional methods like automatic test pattern generation? Because those structural test patterns are not guaranteed to generate a specific image, right? Like for example, when you have MNIST dataset, you have these 10 images, right? 0 to 9. You have one of these classes. Now, if you randomly generate a number or an image, that's not guaranteed to be one of these 10 classes. It can be some totally garbage, which doesn't mean anything. So you will not be able to make sure that your machine learning network is actually classifying the image correctly or not, right? This is very contrasting to how traditional hardware work. Because in traditional hardware, if you have a set of outputs, if those outputs have a different values, you ensure that there's a fault. But that's not always the case for a machine learning network, as I just mentioned. So the size of functional test pattern should be as low as possible. So what we do is we basically have these things. So if you see here, we have these functional test patterns, which we stored in memory, and they will be run in periodic intervals in this accelerator. And then they will detect whether this accelerator is a fault or not. Imagine this like you're doing your body checkup, right? We all go for our health checkup every year to the doctor to measure our blood sugar, our cholesterol, our thyroid, or all these things, right? Now, imagine this is the same thing. So you basically, instead of yearly check, you do periodically, say maybe every 10 minutes or so. You have these functional test patterns. You will run it on the DNA accelerator and will see the outputs. You store their correct prediction. And if these patterns are predicted incorrectly, you will say that, okay, fine, there's a functional safety violation. Now, the question is, which functional test patterns you can use? Now, the obvious answer would be, the first obvious answer would be, use all the patterns in the test data set, right? So if you use MNIST that has 10,000 test patterns, you can use all these 10,000 test patterns and you can run them, and then you can see that, okay, fine, this is, we are getting a functional safety violation or not. Now that's obvious, but what is the problem with that? The problem with that is, first, you need to have a huge test memory. You need to store this test pattern, right? And these patterns are not doing anything to the functionality of the chip apart from testing. So you really don't want to have such a huge memory. The second problem is testing time, right? Because you need to run all these test patterns. That will take huge time to run 10,000 test patterns. So what should we do? We've developed algorithms that will smartly select a subset of these 10,000 test patterns, and those will be run periodically, so that these subset, when you test them, you know that they're doing some functional safety violation or not. Okay, so it's basically, you have a set of 10 patterns. These 10 patterns you will run periodically. So contrasting to 10,000 patterns, 10 patterns will occupy very less memory, 10 patterns will have very less running time. So you can run these test patterns continually, and you can check whether there's a functional safety violation or not, right? Now, the bigger question then arises is, which 10 patterns? If you have 10,000 patterns, you cannot randomly choose 10 patterns, and you cannot do a trial and error method, right? So to address this problem, we propose two methods: model agnostic test pattern selection and model aided test pattern selection, which we're going to discuss next. So the first algorithm is model agnostic test pattern selection. So what do? We form, and so for each image in a class, let me explain using the example of MNIST data set. So suppose we have this 10,000 images of the class 7, right? So we take all these 10,000 images, and then we take the average of them, we take the mean of them, and we consider that the image of class 7, okay? And then for each image, we measure its Euclidean distance from this average image. If the Euclidean distance of it is less than the Euclidean distance of the image of 7 from any other class, we consider it a safe pattern. We don't use it. But if a pattern, like for example, consider the 7 image here. Let me actually take my laser pointer. Yeah, if you consider the 7 image here, you see that the distance from class 7 is 5. The distance from class 1 is 7. Now, due to a fault, what can happen is this pattern might be classified as 1 instead of 7, right? As a result, when this is classified as 1 instead of 7, you can know that there's a fault. So those patterns which are most susceptible to be misclassified in presence of fault, we select them as the model agnostic in the model agnostic algorithm. Okay. Now the problem with model agnostic algorithm we are not considering the model. So we propose a second algorithm, which is model in loop, where basically we consider the model prediction confidence level to select these patterns. So as you can see, the same pattern here, the 7 pattern, has a confidence level of 1 for class of 37% for class of 1 and 40% for class of 7 in a non-faulty environment. This pattern has a confidence level of 2% in class of 1 and 90% in class of 7. So this pattern is less likely to get misclassified in presence of fault. But this pattern is more likely to be misclassified in presence of fault, right? So we then select this pattern for the SBST, for the software-based self-test, okay? So these are the two algorithms we proposed. So these are our results. So as you can see, for the model agnostic test patterns, we choose two thresholds depending on how close it is to its own class based on the Euclidean distance. And the fault coverage we obtained is for the weight and bias fault is not 100%, but for the multiplier and accumulator fault is 100%. So we use three different test sets based on the threshold sizes. As you can see, the test 3 has highest number of patterns, 109 patterns, and that's why it's giving the best results. And the reason that we are getting more coverage in multiplier and accumulator is because multiplier and accumulator, as we saw before, the fault impact is maximal, right? If the fault impact is maximal, it's easy to detect, right? Like, for example, if you consider yourself having a disease where the symptoms are very prominent, right? Like, for example, if you cannot walk or if you have a severe pain, that's easy to detect. On the other hand, if you have a disease where the symptoms are minor, like maybe a small cut in your leg or something, or in your finger, then that might not be detectable. So that's why the weights and bias are not easily detected, okay? So model agnostic patterns, we see that this is performing well, but still it's requiring 109 patterns, which is significantly high. In case of model-aided test patterns, actually, we saw that we could actually use only 10 test patterns and we get 100% coverage. And these are the average number of patterns required to detect. So what does this mean? So that means that for accumulators, you can use that. So almost all the 10 patterns are mispredicted. So what happens is if you have these 10 patterns, so you can run any one of them. We run these 10 patterns, and as soon as one pattern is mispredicted, you know that there's a functional safety violation, and you stop running all the other patterns. So accumulator faults can be rejected much more easily, then multiplier faults, and then the weight and bias. The weight and bias faults need almost 8 patterns to detect, right? So basically, not all patterns fail for weight and bias. So as a result, these test patterns are sufficient and they're pretty good. So you can just store these test patterns and you can run them and you can easily detect these faults. So we did identical experiments for Fashion MNIST and Cypher10 datasets, which are found which will be available in our paper. And you can go over our paper, which is IEEE Explode, and you can see that we had developed these patterns which can detect almost all types of faults. Now, this is our fault coverage analysis. So we see that for Cypher10 with 10 patterns, we can detect almost all faults. We get 100% coverage. With Fashion MNIST, we need some more patterns with like 30 patterns, and with MNIST, we need almost 50 patterns. Okay. So now we talked about test pattern selection, but how about test pattern generation? Can we generate test patterns? Because we are just selecting from the available test patterns, but can we use some mechanism to generate new test patterns which are not there in the training or test data set, which can detect the functional safety violation? So we saw that model-aided patterns furnish high coverage, but are contingent on the network architecture, right? On the other hand, model agnostic patterns are independent of the network, but they do not return high coverage. So this motivates us to generate a self-test pattern with a low cardinality and high coverage irrespective of the underlying model. So this is a background of a neural network that follows a discriminative architecture, right? You get an image X and you predict a label Y. Now, the problem of these models are they're limited by the capability of modeling PX, right? It cannot sample from PX and it cannot generate new images. On the other hand, generative adversarial networks can actually overcome this setback. They can generate new images. So the GAN model consists of two models, a generator and a discriminator. The generator generates new input patterns and the discriminator identifies the images as real or fake. We use this strategy to generate new test patterns. So traditional GANs cannot control the type of images generated. It's difficult to figure out complex relation between latent space and images. The conditional GANs alleviate this drawback. They have the image generation can be made conditional on the class level. So we use conditional GAN for our purpose. So this is a proposed approach. We utilize the GAN-based test generation methodology. The patterns are compared, and we performed a behavioral simulation of Google's TPU. So as you can see, we have a random noise and a class level for generator. And then we have the application data set. We are generating these things, okay? So we introduced permanent bit flip models in the training network parameters, and these are the GAN patterns. So you can see for the Fashion MNIST, we need only 5 patterns. We are needing 30 patterns for model aided. So we need just 5 patterns, and that is sufficient. So as you can see, the FUSA coverage is increasing rapidly. So with a fault rate of 0.4%, we are getting a FUSA coverage of almost 100% with 30 patterns. This is for MNIST. Sorry, this is for Cypher 10. But for Fashion MNIST, with 5 patterns, we're getting high coverage. So as you can clearly see that this GAN-based pattern generation is much better than compared to the previous pattern selection approaches. So now we will talk about mitigation techniques. We talked about the impact of faults. We talked about how to detect faults. Now, what happens when we detect faults? We can either throw away the accelerator, but that results in loss of yield, right? So the other method is to mitigate the faults. How can we mitigate the impact of faults? So for DRAM faults, we propose to use a quality-aware DRAM for energy-controlled accelerators. So what happens? A page error rate in DRAM follows almost a similar trend in bit error rate. So even at high refresh interval, there exist certain pages in the DRAM which manifest 0 errors. So what we do is we have 3 stages here. So with the refresh reduced DRAM, so we look at the error-free pages and the erroneous pages, and we do a mapping of the critical weights to the error-free pages, and the non-critical weights are sent to the erroneous pages. So that what happens if even if there are fault in the erroneous pages, these are non-critical weights and they will not impact the FUSA evaluation as much. One of the things we can do is, for example, the critical compute of the memory bitmaps, we can send to the error-free pages, okay? How about the faults? We looked at the regular components at the MAC unit level. How do we do that? So we propose something called fault-aware pruning, right? So this is post-fabrication testing to identify faults. So once we know where the faulty units are, once we detect, right? How do we take care of these faults? So this is inspired by the DON pruning techniques. So we prune the weights mapped to the faulty MACs to 0. That's the way we do it. We just basically, if there's a faulty MAC unit, we prune the weights to 0. So what we do while manufacturing, we construct a MAC unit. We call this strategy fault-aware pruning or FAP. So we add a multiplexer along with each MAC unit, okay? This is a bypass part. So what happens is, so there's no performance penalty, by the way, it is instantaneous. So what happens is, look at here. When there is a fault, right? When there's a fault, the multiplexer signal is turned on and this MAC unit is bypassed, and the partial sum from the previous layer comes directly to the next layer. So for example, this is the layer 1, this is layer 2, this is layer 3. Since layer 2 is faulty, the partial sum from layer 1 directly comes to layer 3, bypassing layer 2. On the other hand, since this is fault-free, say layer 4 is fault-free, the multiplexer select signal is 0. So you go by the traditional MAC unit and the output is obtained, okay? So in this way, you do not incur any performance penalty and you do not incur any faults due to this faulty MAC unit, okay? This is minus hardware changes with 9% hardware overhead. So the other method we do is fault-aware pruning plus training. So what we do is, once we do this fault-aware pruning, we know which MAC units are faulty. Why can't we just retrain the network? I know I explained at the beginning of the talk that training is always expensive, but retraining is probably not that expensive, right? So we can retrain the network taking into consideration the MAC units that are faulty. So it adapts to faults with new optimized weights and improved classification accuracy, as we'll shortly see. And the training epochs control the final accuracy. So how many epochs you want to retrain the network, that controls the final accuracy, okay? So it's extra one-time test cost per faulty chip. So as you can see here, we have plotted for MNIST and TIMIT, we have plotted the FAP in red and blue and FAP plus T in red. So FAP plus T is FAP plus retraining. So FAP, as you can see, after fault rate of 12%, the accuracy goes down. FAP plus T actually maintains an accuracy even at a very, very high fault rate of 50%. So even if you have a fault rate of 50%, the accelerator will work fine in FAP plus T. So in binary neural networks, so there are a new class of neural networks for low energy overhead, which are binary neural networks. So RAM-based accelerators show promise in executing intensive DNN models in processing in memory, as we were discussing. The binary networks further reduce the storage computation communication cost because you have the weights either +0 or +1 or -1, right? So it's very easy. You do not have to really multiply anything. So one of the popular BNNs is BinaryNet. It's designed for efficient execution. And this is how it works. So basically XNOR. You don't have to multiply. You totally get rid of the multiplication stage here. So let's look at resistive random access memory, RAM basics, which are used here. So these are variable resistance based on length of oxygen atom filament. It's longer filament means longer resistance. A filament length changes due to current flowing through the device. And we have two resistance states, low resistance state, which is called set or LRS, and reset, which is the high resistance state or the HRS. So stuck at faults means either you move from LRS to HRS or from HRS to LRS. Okay, so this is a 1T 1R structure of an RRAM transistor. So this, we proposed a fault-tolerant 2T-TR to our differential bit cell. So we have a state-of-the-art design in XNOR RRAMs. This is the proposed bit cell model, and we proposed this bit cell. So this was we proposed a new bit cell architecture that is by default, by the architecture itself, is resistant to faults. Okay, and we proposed this model called ribbon crossbar array. So instead of the 1T1 architecture, we replace it by 2T-TR architecture. And as you can see, the improvement we obtained for fashion is 97%. So due to fault rate, the accuracy drop for normal XNOR RRAM, which is the state of the art till now, was 11%. In case of our method, which is ribbon, we get 0.4% accuracy drop. So this is a 97% improvement in performance. This paper was actually recently published in ITC, and we presented it last month in ITC. So to conclude my presentation, so we learned that maintaining functional safety in DNA and hardware accelerators is essential. The faults can significantly hurt the classification accuracy. We explored the impact of data path and memory faults in this DNA acceleration for varying bit position, different computation units, and multiple exhaustive data sets. We developed a software-based self-test scheme to detect runtime violation, FUSA violation detection. And we also proposed novel algorithms to select and generate functional test patterns. We deployed these minimal patterns in mission mode to obtain high fault coverage. And we also proposed low overhead mitigation strategies to improve FUSA in DNA accelerators. So that's the end of my talk. If you have any questions, I'll be more than happy to take them now. Thank you.
Thank you. Thank you very much for a great talk. So
I think I finished in time.
yeah. So any questions from our audience? So you can unmute yourself or input your question in the chat box.
I didn't get if your testing was done strictly in training or in training and inference, but in either case, I'm wondering what the overhead, the computational overhead is of testing and sort of what the frequency of testing is.
That's a great question. Can you please tell who is asking that question? I couldn't understand this.
This is Larry O'Gorman. I'm at Bell Labs.
Oh, hi. So, hi, Larry. That's a great question. So we are doing testing at the inference level, because functional safety you are doing when you deploy an accelerator in the mission mode, right? So we assume the training has been done in an offline atmosphere. And when we are saying that when you asked about the frequency of training, it again depends on the computational workload. We need to reduce the workload. That's why we made it just 10 patterns. But how frequently you want to test them, that entirely depends on the particular application. One thing you can do is you can interleave this testing with the regular application. So while the regular application is going on, you can test one pattern at a time. So the whole idea is we have to reduce the number of test patterns. That's why we developed these three algorithms, sorry. Does that answer your question?
Yes, it does. Thank you. And so again, I'm a little bit confused between the training and the inference. When you detect a fault, you showed that in training, you just use a different multiplier, but you skip the multiplier, but that's okay in training. But in inference, if you do that, the performance is going to be degraded. I didn't understand if you're talking about the computational performance or the accuracy performance.
Okay, that's a great question again. So it's entirely on inference, as I said. And if you skip that MAC unit, right, the computation, as I showed you, even for small fault rate, that's actually sufficient. But if you have a higher fault rate atmosphere, like if you are more vulnerable, like for example, space applications, right? These are more vulnerable to faults. So what you can do is then you can stop that, you can have some backup accelerator take care of it. In the meantime, you can do a retraining and deploy the model. You can retrain offline and deploy the model so that this accelerator can take care, and you can sustain the FAP plus T that can sustain a high fault rate up to 50%. I should mention that 50% fault rate is rather impossible. That never happens in real life. But we wanted to make it look at the very worst case scenario, like what is the worst thing that you can sustain?
Right. Okay, thank you.
But thanks for the great questions, Larry. Really appreciate them.
Other questions from our audience?
So I'm going to ask another question unless someone jumps in. I don't want to hog the stage, but my question is, so any recognition system is going to have a non-zero error rate. You are attacking error rates due to the hardware here. Can your methods, do you think, be used for the inherent error in the algorithm as well?
That's a very, very good question, actually, Larry. I'm really glad you asked this question. Not really, because we assume that these networks are pre-trained and deployed, right? So the person who is deploying, like if I'm deploying, I know what the inherent error rate is. I know what patterns will be misclassified due to this inherent error rate. And I have some mechanism to take care of them. My mechanism is entirely due to hardware faults, due to patterns which would be classified correctly in absence of errors, but in absence of faults, but in presence of faults which will be misclassified. Those are the patterns. Those are the things that I'm trying to detect.
Yeah, I get you. Yeah. Okay, that's great. Thank you.
So actually, I have one question about the simulator.
Sure.
Yeah. So I think that's for that one question in the chat box. I think you can answer that.
Can
first.
you please speak? I cannot somehow get rid of my now. Okay.
So if there are hardware Trojan causing fall of Mac, the Trojan didn't trigger all the time. I want to ask whether your proposed test method can cope with hardware Trojan attacks or not. Yes,
I saw that question. That's a good question. So regarding hardware Trojan, it's a very tricky scenario. So if your hardware, since our patterns are running at periodic intervals, and if the Trojan depends on where your Trojan is. If your Trojan is changing the weights for some time, and during that time you are not testing, then it might be difficult to detect. But if the Trojan is changing the accumulator of the multiplied units, then our method can detect them. Does that answer your question? Okay. Thanks for asking the question, Lizu. Yes, Bo, you had a question?
Yeah. So in your current experiment, so you do the simulation on some like the 3-layer MLP and like the MNIST, the fashion MNIST, and the CIFAR. So my question is that, so how about the scalability for such the simulation and for both the data set and for the model?
So we actually did experiments for the GAN-based patterns on not only on MLP, we did on LeNet and other image models also, LeNet, and I think we did on VGG16. In fact, if you see our DRAM experiments, we did them on, let me share the screen here. We did these experiments on, if you can see the slide here, let me share this again. So if you see the slide here, Boy, you can see that we have done LeNet on Fashion MNIST and VGG16 on CIFAR 10. So we actually developed a framework which we're just cleaning up, and we are planning to release in GitHub very soon, which actually not manually, I would say, it actually opens up the model and it will inject a fault and will do these simulations for you. So my students actually developed this model, which you or anyone else in the academic or the research community can take forward and can train any other model and inject faults. We are actually planning to release it very soon on GitHub.
Okay, thank you very much. And another question is about, so like for your photo-aware pruning method. So I was wondering, actually that is also what I discussed with some colleague before. So do you think for the cyclic array-based design, is there any kind of the critical P there or not?
Critical, can you explain the question? I don't
critical P. So that means that such P, so it is kind of much more important than others with respect to the fault tolerance.
Right. That's a great question. Yes, there definitely is, but unfortunately, we haven't done that experiment. We haven't done this analysis. As you can see, this paper is almost 4 years old. We published this in 2018. So we really need to get back to this and do this analysis. That's a very good question. And I think we should be doing this analysis. This analysis should be done if there are some critical piece where we need this, where we should put this multiplexer. That actually will reduce the hardware overhead. So instead of 9%, you can reduce it to say maybe 4 or 5%, right?
Okay. Thank you. Thank you very much.
Thanks for asking these questions.
So is there any other questions from our audience? Okay. So if no more other questions, let's thank our speaker again. So this is very interesting and
thank you.
Very timely talk. And also thank all. I want to thank all of our audience to attend our this week seminar talk. And our next seminar talk will be on next Thursday, because next week I will be in travel to the ICCAT. Okay. So see you November 10th. Okay. Thank you, everyone. Have a great weekend.
You too. Bye.
Thank you, Kanad. Thank you very much.
Thanks for inviting me. Bye.
Bye.